Good morning, everyone. In today's lecture, we will talk about non-uniform magnetic force, and then we will look at sources of magnetic field. How do we generate magnetic field, and how can we calculate the magnetic field that is induced by a wire that has a current going through it? So at the beginning, let's see what are the other shapes of magnetic field distribution within wires that have currents. So all what we have seen so far was calculating the induced force due to the uniform magnetic field that is induced on a wire such that the magnetic field is constant at every point on that wire that has a current. Now here we will be looking at different orientations for the current and for the magnetic field. So in this case, if we have any variation such that the magnetic field is different from one point to another on that wire, in this case, we will have to use the integration. And that's why we have said here that df as a vector equals to I dl, which is a differential element here, represents the length of on that wire cross the magnetic field. So as you can see here, looking at a non-uniform magnetic field in the existence of a straight wire, so my differential element here for the wire is not changing. It's the same from the start to the end of the wire. However, you can see that the magnetic field is varying, and this variation is going to create also a variation in the magnetic force, and that's why we have to use the integration here. The same thing for case B. In case B, we can see that the magnitude is constant. However, the direction of the magnetic field is it changing, which means that the magnetic field induced on that little differential element on this wire is also changing. And that's why we have to use the integration in this case. And also the same for case C, where in case C, although we do have a uniform magnetic field, but as you can see, the curvature that the wire is taking is going to result into a non-uniform force applied on this wire, and that's why in this case we have also to use the integration. So let's start with one of the cases where we can see that we have to use the integration. We have a segment here of wire that has a current I going through. However, the magnetic field represented by this expression as defining a non-uniform magnetic field that is oriented along the y-axis, varying along the x-axis. So here, for example, we can see that the magnetic field along the length of this wire that is decreasing. So from the location on the x-axis, I can see that the magnetic field at every location on the x-axis is it changing. It is inverse proportional to the distance x. So here we need to calculate the force experienced by the wire. So how do we do this? So the first thing we need to define is the variable. What is our variable for this case? And you can see that our variable is x. And what is the infinitesimal element? It is the dl along the x-axis, which is basically going to be dx I hat. What is the magnetic field? The magnetic field is given by this expression. Now, the cross product between my differential element and my magnetic field, because at the end I am looking at dl cross b. So in this case, the magnetic field is along the y-axis j hat. So I am looking at the end as the cross product between I hat and j hat. So in this case, the cross product for I and j, as we have learned earlier, cross product I cross j is going to give me k. So there is no symmetry here to worry about or to make use of. And also the integration limits we have as x, our variable x, varying from this distance from d, x is varying from d to x equals to d plus L, which is the length of this wire. So putting all those together, I know that df equals to I dl cross b. I know b as a vector. I defined my dl also as a vector dx I had. Now I need to integrate from d to d plus L for the cross product of I dl cross b. We said that the cross product between the unit vectors is going to give me k hat. So I will end up with I b, and b here is c over x. So that's why I have ci over x dx k hat. And now taking ci outside, ci as constant here, then I will be integrating with respect to dx over x, and the integration of dx over x is the natural logarithm of x. So here if I said from d to d plus L, and then this is going to be from d to d plus L. Substituting, my answer is going to be the ci natural logarithm of d plus L over d, and the direction is in the z direction. So if we come back to here, we can see that the cross product between this vector and the magnetic field that is pointing upward is going to result into a force that is going in the positive z direction, and the net force is given by this expression. Now let's move on to the second case where we have a uniform magnetic field. However, the wire has been made as a circular path, as you can see here, with this direction. So we have a semicircular wire lies in a plane as shown. It lies in the xy plane, and we have the z pointing out of the page, as you can see here. The wire has a current I in the counterclockwise sense, and it is in a uniform external magnetic field directed along the positive y-axis. What is the direction of the net force acting on the wire? So I'm interested to know the direction of the net force acting on that wire. So the first thing we need to do again is let's look at how is the force is behaving here. Here we have the variable, our variable here, dl. This dl is made of the following. If we look at this element here, that is a differential dl here, we will see that this element is varying according to the variable theta. So my variable is theta on a constant radius. So let me call this radius r. Then my variable is d theta. And the unit vector here is called theta hat. What is theta hat here? Theta hat is the tangential component on the semicircular path here. So this one is my theta hat that is drawn in here. and I have the magnetic field pointing upward. So basically, I'm looking now at two unit vectors. One of them is for the variable theta that is tangential on this circular path, and it is also perpendicular on this radial. So in this case, this is theta. Theta is going to make this unit vector theta hat is going to make an angle of theta with the j hat. So now if I take the cross product of those two unit vectors, as you can see, the angle is varying as well. So the angle is not constant, the angle is varying. When this radial sweeps from theta equals to 0 to 180 degrees, theta is changing as well, which means the cross product between theta hat and j hat are also changing, which is basically the magnitude of the first one times the magnitude of the second one times the sine of the angle in between, and the direction would be perpendicular on the plane that has the theta hat and j hat. So both theta hat and j hat are in the xy plane. So the direction would be perpendicular. So it will be in the either positive z or negative z. So let's look at the right hand rule to know the direction. So if your index finger goes into the theta direction and your middle finger in the j hat direction, you will find that resulting vector from that cross product is pointing in the negative z direction. So here we have theta hat cross j hat equals to sine theta in the direction of minus k hat. So even if you look at any point on this semicircular path, even at this location, you will see that theta hat cross j hat is going to give you sine theta minus k hat. So having said that, now let's go and put all those together to calculate the force. So we said that our variable is theta, our infinitesimal element, the L, is here r, the theta hat, and we have defined theta hat to be the tangential component on this semicircular path right at the location of the radial point. Then the magnetic field is uniform, pointing in the y direction, positive y direction. And we said that now we know what does theta hat across j hat means. It is sine theta and going in the negative z direction. Here, symmetry consideration, expect field to be again in the negative k hat. Integration limit, we're integrating theta from 0 to pi. So we have our differential element that is a vector r d theta, theta hat. We have our magnetic field in the y direction. Then we put the integration f equals to, we integrate from 0 to pi for, just to show you here, theta from 0 to pi for the r d theta, theta hat cross b j hat, and we said that this equals to the cross product of theta hat and j hat is going to result into, so we have here the I as well. We have I, R, B, and then theta hat cross j hat is sine theta minus k hat, and now we need to integrate sine theta. It's going to give me minus cosine theta, then substituting theta from 0 to pi, it's going to give me 2IRB, and the direction is in the negative z direction. So this is how we calculate the force induced on a wire that has a current due to an existence of an external magnetic field. So we have an external magnetic field, we have a wire in this magnetic field that has a current, and that's how we calculate the net magnetic force induced on this wire. Now let's look at the magnetic field that this wire is going to generate in case I have a wire and then I have run a current, a DC current in that wire. What's going to happen? What is this wire going to do? So let's do this experiment. If we bring a wire and then we put compasses around uh, this wire without running any current in this wire, we will see that all those compasses are going to point toward the north field of the earth. So nothing is going to happen on those compasses due to that wire. However, when I run a current in this wire, now this current in that wire is going to induce a magnetic field. This magnetic field now is going to force those compasses to be aligned such that they are always pointing or tangential on the magnetic field lines induced by this wire. So you will see that they will create a path that is circular in shape. So let's look now at this magnetic field. This is the wire that we were talking about. This is now I'm looking here from the top. However, the direction here is different. So here in my case, the current is going, this is the wire. I have the current now going in this direction from the cross. Now, if I look here from the top, this is what I'm going to see. I'm going to see, if I am to, see those lines, this is what's going to happen. The magnetic field generated by this wire is going to be circular in shapes, as you see here. The direction of this magnetic field is defined by the right-hand rule. Now, here we have the current going straight, so we will use the thumb for the current, and the fingers will point toward the direction of the magnetic field. So in this case, if you put your thumb into the page, you will see that your fingers are going to curl such that the direction for the magnetic field is clockwise. Now, this is the magnetic field lines. They look circular, as you can see here. However, the direction of the magnetic field at every point on those lines is indeed the tangential component, as we can see here, on that circular path. So here, the magnetic field is pointing this way. At this point, the magnetic field is pointing that way. At this point, the magnetic field tangential and pointing in this direction. Again, here the electric current is going down, as you can see, and I am looking from the top. I'm looking from the top. I'm seeing the current going down. That's why I put X here. And based on the right hand rule, I can see that the field lines for the magnetic field are going clockwise. So, what is the relationship between the magnetic field and the current? And how far am I from this wire? We have found that the magnetic field is proportional to the current. So The greater the current, the greater the magnetic field. And we have also found that the magnetic field is inverse proportional to the distance squared. The magnetic field is different than the electric field. It is not along the line between the differential element and the point of interest. As you can see here, the magnetic field direction is the cross product of my differential element and the unit vector of the displacement vector. If we put the expression for the magnetic field together, then we will find that the magnetic field is mu naught I divided by 4 pi integration of dl vector cross r hat divided by r squared. So this is the expression for the Biot-Savart law that defines the magnetic field due to a current going into a wire. And this is the general case. This is the point of interest. The r vector and my dl vector, they are both in the yz plane. And in this case, due to the cross product between my differential element dl and the unit vector of r, the magnetic field has to be perpendicular on that plane. And if I use the right hand rule where the thumb is pointing toward the current and the fingers are curling in the direction of the magnetic field, right at this location to the right here, I can see that the magnetic field is pointing in the direction of negative x-axis. So here, that's why I have at this point my direction for the magnetic field to be in the direction of minus I hat. So this is the general expression for the Biot-Savart law. And here, mu naught is the permeability of the free space that's given as 4 pi 10 to the power minus 7 Newton second square per Coulomb squared. And this is my differential element from the wire, and this is my displacement vector and the unit vector for this displacement vector that we will be using as we did earlier when we calculated the electric field to calculate the magnetic field for a wire of current. This setup here, we have our wire that is oriented along the y-axis, and we are interested to calculate the magnetic field at a distance of x from the midpoint of this wire. This wire has a length of 2a, so this is a and minus a on the y-axis, and this r is my displacement vector here between the point of interest that I would like to calculate the magnetic field at and my differential element dl. Okay, so let's see. Again, this is the expression for the Biot-Savart. This is the general expression that we will need to use. This is the dB vector. So I will derive this. So let me put first my wire. And I have the current I going up this way, and this is my X, this is my Y, and again my Z is out of the page. So if I take this as my differential element, the infinitesimal here. So this is my dl vector. So my variable is y. So my differential element here would be dy j hat. So this is number one. Number one, my variable is y. So my differential element is dy j hat. Then I have the point here. This one is x. And the distance from here, from my differential element to the point of interest, is r vector. And I need to calculate the magnetic field right at this point. Let me call this one P. So here I have my vector R is, so if this one is Y, so my vector R is made of two vectors. Number one, Y minus J hat plus X I hat. If you recall, we will need the R vector. Number three, I'll put everything together. I have dB equals to mu naught I over 4 pi dl cross r hat over r squared. Now, I know that r hat is r vector divided by the magnitude, and I have found r vector, then r hat is y minus j plus x I divided by r. Now, if I put everything together, now the integration is going to be y varying from minus a to plus a, integration limit. So I have here b equals to integration y from minus a to plus a mu naught I divided by 4 pi. We said that dl is dy j hat cross y minus j plus x I divided now by r cubed. And we said that if this is the vector r here, I can find the magnitude right away, which basically going to be x squared plus y squared, as simple as this. I need the magnitude as well. So now I can put everything together. B equals 2. So you can see there's not much difference with the electric field that we have derived, except that here we're using the cross product. So it is similar. I have y from minus a to plus a mu naught I divided by 4 pi. Then the cross product between j and j is 0. Any unit vector that you take the cross product with itself is going to give you 0. Why is this? Because it is j cross j is going to be 1 times sine. The angle is 0, so this is going to give you 0, right? So I'm not going to, I will get a 0 from here. Then I only had the xi. So di j hat cross x I hat is going to give me dy x dy, and the answer is minus k hat divided by x squared plus y squared 3 over 2. So if you recall, this is the same function that we have seen using the integral, the table of integrals. We can find now the dy over x squared plus y squared, and this is going to be equal to y over x squared plus y squared, which is the same function that we have seen in the electric field. So here b equals to mu naught can go outside, 4 pi can go outside as well. So now this is going to result into also the x can go outside. So now I have y divided by x squared plus y squared minus a to a. X squared is a constant, so it can go outside. So this is going to result into b equals to mu naught I. X is going to cancel over 4 pi x, and then this is going to be a divided by x squared plus a squared minus a divided by x squared plus a squared, and we don't need to forget the minus k hat. So b equals to mu naught I. So this is going to be now a minus a is 2a. 2 will cancel with the 4, so this is 2 pi x, a over x squared plus a squared minus k hat. So you can see that the direction of the magnetic field is pointing in the negative z axis, right? So this is the magnetic field due to a finite wire that has a current I going through. Again, so this is how we derive it. Here there's also a second approach for calculating the cross product here between J and R. Remember, we said that for J and R, it is sine theta. The angle between them is theta. So sine theta minus k hat. Then you can substitute sine with x over R. So here, if we look here, so this angle here is theta. This angle here is pi minus theta, which where basically we have sine theta equals to sine pi minus theta, and then this is going to be x divided by r. Then you can substitute r magnitude with whatever we have calculated there. R magnitude as square root of x squared plus y squared. So this is going to take you to the same results that we have derived ourselves. Okay, so now let's look at this example here. This is the wire that has a current. This wire that has a current is generating a magnetic field. This magnetic field, we have learned, if we have this vector r, the displacement vector, in the same plane with the dl that is right now in the xy plane. If they are in the xy plane, then I have the magnetic field based on the right hand rule at this point, thumb pointing up, the fingers are curling such that the magnetic field in this point, in this side of the wire, is pointing into the page. Now notice, and again, due to the right hand rules, the magnetic field on the left side of the wire is pointing out of the page, right? So this is another observation that you need to be aware of. Based on the right hand rule, if you look at the right side of the wire and the left side of the wire, based on the right hand rule, the right side of the wire, the magnetic field is pointing into the page. Based on the right hand rules, the left side, the magnetic field on the left side of the wire is pointing out of the page. Now, if we have this wire that has this current going up this way, then the magnetic field, assuming that this wire is greater than the distances between those points A to D and this wire, then I can say that the magnetic field at the point C is the greatest. If I am to compare those points A to D, then comes A, then comes B, then comes D. Why is that? Because it is inverse proportional to the distance squared. So C would be the greatest, and then D would be the smallest magnetic field. Don't forget that the cross product here, as long as you have the magnetic field perpendicular on the plane that has the displacement vector and the dl, the magnetic field will have the same direction, will not change. Now let's look at this question. In this question, we have the magnetic field due to a current in the length of wire shown. So we're only looking at this element, only the magnetic field due to this dl. This is small infinitesimal element here, this differential length. We need to rank the points A, B, and C in terms of the magnitude of the magnetic field due to the current in this location only. So I am comparing the magnetic field, the magnitude of the magnetic field at A, B, and C due to this differential element only, not the whole current, only this differential element. So based on the distance, I can see that B has the smallest distance, then comes C, and A in this case would be 0. Why A is 0? Because if I look at the differential element here, dl, and I look at the vector, the displacement vector here, the angle between the displacement vector and the differential element here, theta, is 0, which basically this is going to result into a cross product of 0. Why? Because sine theta is 0, then sine theta is 0, and this is going to result into a magnetic field being 0.